simplest case, which is when of the state space, when you have just your Hilbert space is 2-dimension, also known as like the quantum system, also known as 2-level system, or spin 1/2. But for the sake of for the quantum information jargon, people just call it a qubit. And it's the thing that we have been doing and we will continue doing in this lecture is to look at what we can do with the operator space, right? Which is in matrix form, is they're really just a set of 2x2 matrices, a set of linear operators, and a lot of things can be solved exactly in the case of qubit. And so this sort of become a new standard for toy example in quantum theory. It used to be harmonic oscillator before, but that you have an infinite dimensional Hilbert space. Now, if you can figure out something with a harmonic oscillator, then maybe you can start thinking about qubit, for example. Yeah, and when you look at these examples in the literature, sometimes it can be kind of like outrageous. It's like, why can we do this? For example, the paper of John Presque and Patrick Hayden, they try to think about what would happen if information fall into a black hole. And in that paper, basically, so they would just write the introduction, write down the motivation of like what gravitational and stringy people, quantum gravity people think about it, and then they'll say, okay, let the black hole be a collection of n qubits, and then you throw more qubits into it, or something like that. So yeah, actual researchers do like use qubits, actually multiple qubits, as a toy example of a lot of things, a lot of physics. So we have, board is very clean. So last time we laid out by basically saying that the set of Pauli matrices which in the quantum information jargon, its notations, people would get lazy. Let's call this XYZ, capital XYZ. They form an orthogonal basis for, well, if you think of them as matrices, then they form a basis for the space of 2x2 matrices. Yeah, right, like this. If the coefficients are complex, so like all complex matrices, if you take complex linear combination of them, or if you only take real linear combination of them, then they become the set of our Hermitian matrices. Real linear combination. And the way that we wrote it last time is that I assign A1, A2, A3 into components of a 3-dimensional vector, and then I dot it into this vector of operator sigma xyz. So in fact, since we already know that, okay, so this vector doesn't have to be normalized, right? But we know that if this vector is normalized, this would be an observable with eigenvalue plus or minus 1, right? So with the eigenvector, this and this, right? This for plus 1, this for minus 1. And so if A is diagonalizable, then it's pretty easy to get the information about the eigenvector and eigenvalue, right? So I can factor out the magnitude of the vector and then write it like this, right? So let's say if the, okay, let's say this. If everything is real, then it's easy to see that A must be Hermitian, right? So it is diagonalizable. And well, what would be its eigenvectors and eigenvalues? So since the identity is diagonal in every basis, right? So the eigenvectors at least must be the same eigenvectors as this guy. And then the eigenvalues is just whatever, so like a plus minus this, right? Let's say Hermitian therefore diagonalizable. But if the coefficients A can be complex, then is it the case that you can always diagonalize the matrix A? Well, so if it's always, then where does the like matrix that are not diagonalizable goes? So last time we learned the if and only if condition for operator to be diagonalizable, right? So what is that condition? Huh? No, I mean that is true, but it's trivial. Yeah. Yeah, so like being Hermitian, being unitary are subcases of this normal, right? And so there must be some A that is not normal, right? And well, I'm not gonna check it. In fact, I've never checked it, but because it's a bit tedious. But it's one of the homework problems. For case 2, if you allow these to be complex, then not always diagonalizable. So at least it's easy to see that if the coefficients are complex, then this would not be Hermitian, right? The question would then be, well, what would be the condition that they are normal operators? And this is for a qubit, you will work out in over 2.2. So the second problem, right? And then yeah, homework 2.3 asks you about the usual example of non-operators that are not normal, which is this guy, the raising and lowering operator. And how can you see that they form the basis of all Hermitian operators? So to say in another way, is there any Hermitian operator that cannot be written in this way for 2x2? No, right? So you have to, but how to think about this? And you have to think of the space of Hermitian operator as a vector space first, right? So what is the dimension? So now the question, so it's different, right? So if you think of complex matrices, like complex 2x2 matrices, and you allow the coefficient to be complex, then it's clearly 4-dimensional because you have 4 complex number. But now if you think of Hermitian operator as vector space, as a real vector space, then you have to count them, actually think about counting the dimension, which turned out to be 4 anyway, but right? So in general, what is the dimension? So yeah, I think it's better to give some notations to this space. So in, okay, I don't remember what I gave in the homework, but in Nielsen and Chuang, I think they denote like this, the space of linear operators over the Hilbert space. In the literature, and I put this as a footnote in the homework, that you can find other notation as well. Okay, I cannot write math on Blackboard. Yeah, this notation B stands for, it's meant to signify bounded linear operators. So it's important in infinite dimension that you might want to restrict to just bounded linear operators. And the definition of bounded linear operator is that when I act on, so let's see, basically that this is finite. So for in infinite dimension, in the infinite dimensional Hilbert space, you know that this might not be the case. For example, the position operator, right? Because it's basically, if I add this, well, I'm being like fast and loose, being a bit illegal now. If I say that this is the position eigenket, which is not really a ket, and then an act by the position operator, then is it the eigenvalue is whatever in X, right? Which doesn't have to be bounded. For finite dimensional space, everything is bounded, so we are happy. There is I guess no standard notation for the space of Hermitian matrices or unitary matrices. For me personally, I would just put a double line. So this is the math BB in LaTeX. Then I will just do the same, so math BBU and for unitary. Yeah, but some people might say something like, for example, so what we just talk about is what is the dimension of this guy, right? So how would you count it? So if you think of the matrix form, right, or Hermitian matrix, well, what? Okay, so how many real parameters? So as a, okay, I should emphasize as a real vector space. So how would you count this? So what is the, so if you look at the definition of permission operators, right? So the dagger must be the same. So in matrix form, is that the complex conjugate transpose must be the same. So that means the diagonal must be real. And so you get D. So suppose that suppose the dimension of the Hilbert space is D. So we get D parameter here, right? So for the off-diagonal terms, since the complex conjugate transpose has to be the same, so for example, the upper triangular element will determine the lower of diagonal terms too, right? And so how many of these, how many real parameters would you need to describe this? Then basically you just sum, right? So either in your head or in your paper. Right. So there, I just count the complex numbers first. So, okay, so how would you count that? Personally, I would just count it like this, right? I would just like get one thing over here, but then I have to sum over the the number of elements until the first of diagonal terms, and this has the -1, right? So it's basically a sum of k from 1 to d -1, and you know how to sum this in your head. Yeah, something like that, right? Because I'm summing over this, right? And then the trick is I just imagine the other one and then sum to d, and then yeah, something like this. So yeah, there are d -1 and then d, the sum of d over 2. But this is the number of complex parameters. So if you want the real parameter, then I just take out the 2, right? So now, so what is the total dimension? This is d squared minus d. So then if I add the number of diagonal elements, then it's d squared again. Yeah. So d squared. And so, for example, for 2 by 2 Hermitian matrices, the dimension would just be 4, right? And then the size of the number of elements in this orthogonal basis is already 4. So it must be a basis. Uh, so before I talk about something else, maybe I just give some extra remarks. Because a lot of time I got the question that's why we are using Pauli matrices. Uh, so there are other bases for the operator space, right? For example, in the first problem, you are asked about, for example, using projectors, one-dimensional projector as basis. But what is so nice about Pauli matrices? Well, at least for qubit, it sort of correspond to three dimensionals in the space. So basically, so Pauli, so when you can generalize this to higher dimension, in the sense that I can always find a set of let's see. Okay, sorry. If you, let's see, so there is, in higher dimension, actually you cannot generalize all the properties of the Pauli matrix. You can bring something along with you, and then you have to throw out something. In particular, Pauli matrices are Hermitian, right? They are also unitary, and then the basis is also special, that this set of bases consists of the identity and then some other traceless linear operators. So in fact, you cannot do this in higher dimension. Like if you have 3 dimensions, 4 dimensions, and well, maybe you can ask what is special about this, right? And I guess it ultimately depends on the application. But for example, if I think about okay, one interpretation that I have in mind is that tracelet operators, you can think of them as vectors in the sense of differential geometry. So if you want to do differential geometry on the state space, in the sense that, so if I have like state at time t, and then maybe I want to write like a equation of motion of differential operation, I can, as an intermediate step, maybe I can think of the delta, right? The difference between the state at time t and the state at time like t plus delta or something. So maybe I want to write the other way around. Okay, delta t. Yeah, so it's kind of awkward writing this because usually people would just think about the time evolution of density metrics instead. But the point is that, okay, so like if I divide by delta t and take the limits delta t going to 0, then it's the first derivative, right? For the equation of motion, you would have something on the right hand side that this is equal to something. But and the point is that whatever operator that you write on the right hand side must be traceless, right? Because if I take the trace of this, it's just a linear operator. It's just a the trace is a linear map, so it's equal to the trace of this minus the trace of this, and the trace is well, for projector it's always the same, which is 1, right? So this must be equal to some traceless thing on the other side. And in terms of differential geometry, you can sort of think of this motion as like as you're moving along some direction in the state space, right? And then this derivative would correspond to something like directional derivative. Yeah, so I guess that's one way to think about it is maybe you can get, I don't have it on the top of my head, maybe you can get the geometric interpretation of like the relation between determinant and trace in this way. What is that? You know, right? Like if I have if I have like e to the a, then this is e to the trace a. Right. Yeah, and for qubits or multiple qubits, if you take the tensor product of Pauli matrices together, so I haven't talked about tensor product yet, but if you take if you think about the space of linear operators for multiple qubits, and then just take the tensor product, use the new basis, which is the tensor product of all possible Pauli matrices on like each qubit, then that would become an orthogonal basis on that big space too, and they would still be Hermitian and unitary. But if I have higher dimensional system, like three level system, four level system, and I want to define something like a Pauli matrices on that, you could sort of have both property at the same time, I guess sometimes, but usually some well-known generalization is that if you want the Hermitian property, then you can use the so-called Gell-Mann matrices. And this is like just the Hermitian generalization of the Pauli. And if you want the unitary, then you just use the generalized Pauli matrix. It doesn't really have a name, but in Wikipedia it's also called clock and shift matrix, in the sense that so for qubits, I have, if I act on the 0 or 1 basis, 0 or 1. So if I let C act on this, then depends on the value J here, I would get some sign, right? So plus or minus 1. And then if I add on it with X, then I get I will flip the value of the qubit. So here I don't know how to write it, so I just write addition mod 2. If it's already 1, then 1 plus 1 is 0. So by clock and shift matrix, I mean that in higher dimension, you can define something similar to this. So you sort of just define 2 sets of operators. One, so you fix like a computational basis. And then one set of operators called like generalized Z. This would give some phase based on the value of the Q dit for D dimension. And then the generalized X would then shift the value, just march the value along. But you have a periodic boundary condition, right? So if you're on the last basis, then you move back to the basis. And then all other operators, like for qubits, we have Y, but Y is just the product of X and Z up to some phase. And you can do the same thing here as well. So when you use when you collect out the product of X, generalized X and Z in this way, let's see. Okay, I don't remember if it's both Y and Heisenberg, or their name usually come together. But yeah, this would be some a generalized of the Y Heisenberg algebra onto higher on. Well, actually, because when you think about Y Heisenberg algebra, you usually think about this thing, right? And usually there's H bar, but people just set H bar to 1. But mathematicians usually don't like this kind of thing. Like, for example, if I understand correctly, if you go to like a course like by Frederick Schuller on YouTube, and he teaches like quantum mechanics for mathematicians, he will say that this does not exist. Simply is related to the fact that operators here are not bounded, and also somewhat related to the way that we learn that in finite dimension the trace of any commutator is 0, right? But here is clearly not the case for here. So usually mathematicians find it to be more comfortable to not consider X and P, but consider exponential of X and P, e to the ix, and then some scalar xq. Okay. And since these are unitary, so even though the eigenvalues of these are unbounded, just go from like minus infinity to plus infinity, right? But when you make it into a unitary operator, then the eigenvalue, the spectrum wrap around, and it's become finite. And so people like to, some mathematicians like to think of the commutation relations in terms of the commutation relation of like these guys instead. Well, not even the computation relations, but yeah, the equivalence of it in group theory. And unitary like this, they are called like the element of like Y Heisenberg group. And so one of these, so if I write one for when you exponentiate the position operator, I can write one where I exponentiate the momentum operator too, right? So maybe make it more symmetric, like AB or something. And these two would be the continuous analog of this guy. Well, maybe it's the other way around. Maybe I have to swap arrow, but it's just algebra. Yeah, so you can also like, so people also play around with this kind of thing where you sort of have a discrete structure in finite dimensional Hilbert space. It's like kind of like the what we used to in infinite dimensional Hilbert space. Yeah, there are a lot of interesting thing about this. And there is actually let's see. So I'm not sure if it's in every dimension, but at least in odd dimension you can have operator bases that are both Hermitian and unitary as well. But does not include the identity. Fun fact. Yeah. Yeah. So the example I talk about is just the phase point operator of the Wigner discrete Wigner function. Okay, so that's just some entertainment. Now back to the actuals. So before we leave this topic, I also want to say something about unitary operators for qubits, because here it's clear that I can get any Hermitian operator in this way, right? And here is not so clear. It's something that you have to work out. What are the conditions for normal operators? But then there's important unitary operators would be an important subclass of normal operator, right? So we're gonna talk about that and see the what unitary operator does in the block sphere picture. But actually, I will not show the whole thing because it's part of the homework as well. It's 0.4 or 0.5. Let's see. Homework point something. So I don't remember if it's an assumption or something you need to show, but you will see something like this in the homework. So suppose that I act on the vectors. So okay, so just to clarify, this is element by element action, right? So this is a vector, a vector of 3 Pauli's operators, and here it just means that I have sigma x, y, z, and then I act on it like this, right? You see that this act on the vector itself as a rotation operator around some axis, which I call n here, and with the angle theta. In particular, just to remind you, probably seen it from some other course, this is an orthogonal matrix. Right. So it's a matrix that acts on a real vector. So it's a real matrix one first of all, and the it's kind of like unitary, except that instead of permission conjugate, the transpose of it is the inverse. Yeah. And the main property is that it's preserve dot product, right? So preserve real inner product. And for it to be a proper rotation, it's also true that the determinant of this is 1 as well, because for matrix, transformation matrix that are determinant plus minus 1, then those are reflection. So this reflection is not continuous, but here the unitary is continuous, so it's become a rotation matrix. And of course, there has to be some R here, which would be determined by the permission operator, that the Hamiltonian that you exponentiate to get the unitary, because that would be some linear combination of x, y, and z, right? Pop sigma x, y, and z. So actually, from this, I can show that. So let's see. We can show that if I rotate, okay, maybe I want, okay, I'm not gonna use n again, so it's fine. I can, so this n and that n is different. Okay. So from this, we can show, for example, that if I apply unitary corresponding to the rotation R onto the state, then it really rotate the vector on block sphere. In the sense that this is an eigenvector, so like +1 eigenvector of this observable, this spin observable in this direction, right? And then we can show that, which I'm gonna do, is that this new rotated vector is also +1 eigenvector, but of the observable that in which this has been rotated. And do I need? Yeah, so just this. So is it clear what we are gonna do here? Yeah. Because in, yeah, just to say it again, because in the Hilbert space, I can apply unitary operator to a state vector and it becomes another state vector, right? So here I just want to show the geometrical interpretation that if I do this, then it's actually a rotation, a three-dimensional rotation on the block sphere, in the sense that this vector actually has been rotated. However, this vector is not a state vector, right? So it's more that this is an observable, and so we are just rotating to an eigenvector of the new rotated observable. Okay, so I first I can write down, suppose that I have a dot product commutative, so I can write on the left, on the right. And if I act on it by this. So this is opposite to what I wrote down there. So it's the operator acts, the unitary operator acts on the operator, right? The sigma, because M really is just a vector. I mean, a vector in a very classical sense. It's not an operator. Right? Vector of scalar. And so according to that, I have to act on sigma with R inverse. Right? Because I switched the dagger from two sides here. And so it's this. But the transpose is like an adjoint because you can move it to the other side, and then takes an inverse of that. So now we can show that, say, if I act on, so let's see, if I now consider this operator, now I just want to show that it is an eigenvector, a +1 eigenvector of the new operator, right? So if I so this is rotated observable. Well, so I can use this equation, right, and then pull out the unitary matrix on the left and right side. Okay. I shouldn't write M there. So in this cancel, and then when sigma in the n direction acts on the eigenvector, f on n is just a +1 eigenvector, right? So it's +1, and the sigma disappear. And that's it. So we have shown, right, that this vector is actually an eigenvector of the rotator. But again, what came before this, you would play with it in the homework problem. Yeah, so time evolution of a quantum state, a qubit quantum state, actually do correspond to some rotation on the Bloch sphere. And actually what determined the rotation, what determined the rotation would be the Hamiltonian, right? So for example, what would be the Hamiltonian that drive rotation around the C axis, for example? Let me do that something. So, choice question, right? So the X, three choices are X, Y, and Z, or you can have identity, but it doesn't do anything. Z, right? And why is that? Well, for example, you can think of what happens to the eigenstates of Z, right? Which is the North Pole and the South Pole. Right. Okay. So this again is -0. So if I let, okay, I'm gonna ignore the T and the S bar. So if I have some parameter, let's say alpha, and then I have z. What would be, what would you get from from the thing this unitary acts on the state, the eigenstate of z? Yeah, so it will depend on the j, right? Right. So this would be the eigenvalue. So does it change the state? No, right? Because it's this is just a global phase. This is an unphysical global phase. So surely the geometrical picture of this rotation must rotate around the z-axis, because it doesn't do anything to the vector that point to or away from the z-axis. This is true in general. So in general, I don't remember how I wrote it in the homework. There may be some factor here. So you have the part of unitary operator that come from exponentiating the linear combination of the Pauli matrices, and then you can have something that come from exponentiating the identity matrix, but that would just be a global phase. And you can ignore it. However, well, a quick comment about global phase of a unitary operator. So for the state, we can eliminate the global phase, right? For example, by forming the projector, the outer product of the state instead. But here, for unitary, you sort of always has the ambiguity in the sense that if you let the unitary with a global phase act on the outer product, like the global phase will disappear as well, right? So yeah, either the global phase from the state or global phase from the unitary would disappear like this. But yeah, this is only when you write in, you express it as like usually acting on a state. But for example, if you want to say approximate a unitary operator in like quantum computing, for example. So for example, maybe you have some unitary u that you want to approximate, but you cannot do it exactly. So maybe you want to control the error by, for example, computing the norm of the difference between b and u. But the problem is that it doesn't matter. Like if I can approximate, if I can find v that is a good approximation of this, is as good as if I don't have a phase here, right? So somehow, yeah, when you do this kind of like approximation, you sort of have to care about this as well. Yeah. It's not so, not relevant to us right now or in this course, but yeah, in like research, yeah, this is a nuisance. Yeah, it just means something annoying that you have to think about. Yeah, for example, if you want to optimize this, like finding the closest approximation, then you have to consider the whole space that depends on the global phase delta as well. So example of this kind of rotation in physics. The usual example is that we have spin 1/2 particle, right? And then the particle, like an electron, would already have its intrinsic magnetic moment, so it interacts with magnetic field, and this is exactly how the physics. So the physics goes into the time evolution through the Hamiltonian, right? So for example, example, spin 1/2 in the magnetic field. So the Hamiltonian here would have this form. So this is just a classical form of the Hamiltonian, right? And in quantum, this mu is written in term is as a product of, okay, so everything is a vector, except that this is a vector of operators, right? So the not the Pauli sigma xyz is the spin s, which is the Pauli times h bar over 2, and over 2 is just because it's spin 1/2. This is the gyromagnetic ratio, which I don't remember. Who remember? I think for electron is like 2 something. I don't, yeah. So if I write it all out in terms of the Pauli matrices, then you have this part. So this so to write in the familiar form, I would just separate the magnitude of the magnetic field out, right? And then I have a unit vector pointing in the direction of the magnetic field, and this is so let's do that. Right. And people would call this the Larmor frequency. Because it actually has the unit of frequency, omega. So then once this is the unit vector, then this is the usual spin observable, right? That we are by now already familiar with, that has eigenvalue plus or minus 1. So the energy of the whole thing would just be the eigenvalue, the whole eigenvalue, right? So like plus or minus 1 time this. So for example, the minus sign here would mean that the plus 1 eigenstate is the ground state. So for example, if I have magnetic field in the z direction, like B, and let's say that the state at time t or time 0 is the plus state, which is defined as a uniform superposition, the equal superposition of the 0 and 1. The magnetic field will drive this state around, right? We just rotate it. So if you work it out, you will find that this basically rotated the plus minus state. So the minus state is the thing in the back here, right? So it will oscillate in this plus minus basis. It will oscillate around these two vectors. With this kind of frequency over 2. And so for example, if you look at the probability, so maybe just probability of to find the state in plus or minus state as a function of time. Yeah, basically you will find that this Larmor frequency is actually the frequency of this rotation. Yeah, so you will see the populations kind of goes yeah, up and down like that. Okay. Any question, comment so far? No, here I just mean that the magnetic field, the unit vector, the direction is pointing in the z direction. Yeah. Yeah. Otherwise, I just have to. Yeah, it's kind of boring to write. I just. Yeah. Yeah. So that was about a qubit. Or was that it? Well, this is the qubit according to our quantum mechanics 101 knowledge, right? But now we're gonna generalize the phase space to also include the so-called mixed states. So for example, in NMR or MRI, right. I've never known the actual history of. I don't know the actual history of the name, but I had some physics teacher told me, perhaps jokingly, that so this is nuclear magnetic resonance, right? And then he said, maybe jokingly, that well, when you apply it in the medical context, then people is afraid of the word nuclear, and so you just take the nuclear out, and now it's just magnetic resonance imaging. Imaging. So just yeah, taking a photo basically. So what happens in the MRI is that do you know how the MRI works? So basically, so what it's trying to do is to try to distinguish different tissues or different like components in your body and stuff like that, right? And well, okay, I kind of forget too how it works. Maybe it depends on the component of water or something. But uh, basically, the whole thing that MRI does is that it sends a strong magnetic field to uh, to your body, which is basically a bunch of tiny magnets now because it has like particles and stuff. It's like electrons and stuff. Uh, and that would just like uh, induce the spin of like electrons to point in the same direction. And then after that, they look at the decay of this signal from the spin direction. And what I mean is that, in a sense, what they see, I guess they're not actually like measuring the probability of being in a plus state, but just to make an analogy, if they do that, actually, they would see something like this instead. And so this is sort of like the spin vector. It's kind of like, well, it's kind of like it doesn't have a spin that is really pointing in any direction. But that's sort of, I guess, the wrong way to put it. Is kind of more like unpolarized light. In the sense that, well, so when you learn, or at least when I learn about when people are talking about like unpolarized light in undergrad, I was like, at first I was very confused because, well, light is polarized. So what do you mean by unpolarized light? Well, so it turns out that it's more of a statistical meaning. It's like you have equal mixture of like up and down polarized light, for example. In this case, it's also the case that after a while, actually, there's like an equal mixture of spin up and spin down. And so they sort of don't see the signal. And here's what sort of we're gonna manage with the generalization to the so-called mixed state. How much time we have left? It's 20 minutes. Plenty. We'll switch gear a bit and think back to what I call a classical state space, but state space of what, right? So in classical physics, when we say state space, you probably think of something like phase space instead. But here I would just be talking about the space of probability theory. Meaning the space of all possible probability distributions, which usually people don't usually think about it explicitly because they have just some model, right? So if I go back sort of to the very first lecture, that from the data, people would statistician would assign some probabilistic model to the data, but usually they do not consider like all possible probability distributions. They will just focus on some simple one that they can understand. They can parameterize, like the Gaussian or something like that, right? Which has like just 2 parameters. But here, if we consider all possible probability distributions, but of course, that's kind of too much if the sample space is infinite. So suppose we have a coin. So there's 2 alternatives. So what would the state space be like in terms of what would be what are our possible probability distributions for 2 outcomes? Well, it just be that's one probability distribution, right? But there are more than that, right? Yes. So we have one parameter, right, for this. The distribution is just p and minus p. Well, I'm not sure like what bracket I should put. And so the state space here is just a lie, right? In the sense that if I have the property p1, p2, this is the lie such that all the p and 1 minus p sum to 1. So now what's the shape? What if we have 3 alternatives? Then this sort of just an obvious generalization of this kind of thing, right? So I will have a plane, right? Plane, but so this is the P1 plus P2 plus P3 equal 1 plane, but only in the first quadrant, right? So this, yeah, just because the probability has to be positive. Yeah. And just to emphasize, just the plane, right? Just the plane is not the body behind the plane. And so this sort of obviously generalized in higher dimensions, and this kind of shape is called the simplex. It's called the probability simplex. So for plural, is probability simplices. And it's a pretty special shape in the sense that it's closed and bounded convex set. And recall that okay, so everyone understand like what each point, what like points on this plane mean, right? So here, for example, it just be the distribution such that all the probability mass just pile up on the third alternative, right? And the same for both for the other 2 points. And then anything else inside here would be a mixture of some of the 3 alternative, right? And actually, we will call these spatial point pure states. And then everything else are mixture. However, well, so here I use the word state. Now, synonymous with the word distribution, right? If you compare this use of word state for like state in physics, they would have different meaning. It would be like some kind of like, well, maybe not oxymoron, but this is not quite the meaning of state in physics. Because, well, what is the state in physics? The way that physicists usually introduce this is, for example, for new like classical mechanics, they'll say that for a point particle, the state is determined by x and p, right? The position and momentum, and this is why we say that the phase space is the state space for classical dynamics. But the sense that it is a state, usually in physics, we say that the state variable, for example, so like the state would be determined by the set of variables that provide a complete information that, you know, complete in sense it let you determine the state. This is what they call the state, right? But here, well, the thing inside the mixture is not really a state in that sense, because if you have a complete information, then you would necessarily, so if you're not ignorant of like the what alternative occurred, then naturally you would be in one of these 3 points. And so the thing inside would not be called a state. However, I think, so we'll see that the name mixed state will be used in quantum mechanics. And yeah, that's just what people call it. So sort of have to follow them. So back to this point. So the simplex is a convex set. If you recall, the convex set is like any set, right? That if I draw a line between any 2 points, then every point on the line is still lies in the set. Okay. For example, like this would not be a set. But in our case, this shape is not only convex. And by the way, the convexity here precisely mean that we can make mixtures of this point in the boundary, right? Which we call pure states, but I will clarify later. But what's special is that this is also closed and bounded. And actually, for all this property, if it's closed and bounded convex set, then is a fact that every point inside this set can be written as a mixture, as a convex combination of extreme points. Convex combination. Extreme points or extremal points, which here we call the pure states. Yeah, this is from a few weeks ago, right? So it's a case of linear combination when the coefficient is real, positive, and sum to 1. So the statistical meaning of it is really just this is like a probabilistic mixture, right? So in the example that I talked about before, suppose that I toss a coin, and then it can have probability of being head or tail. But if I consider, for example, just the probability of getting the outcome head, but then on top of that, if I'm not sure, so the example there, right, is that I have PAPB, which is this is like the probability of getting the outcome head for, so A maybe American coin, and B is like British coin. So then I'm not, and then I say, okay, I'm not sure which coin is the coin that I have, and I believe it's like the American coin with probability lambda, and then this is probability minus 1 minus lambda. So this taking convex combination will give you another distribution, right? That's we think of it sort of like a mixture between two or more distributions. So it's sort of like a randomness on top of randomness. But in the end, you can sort of lump it all together, and it's all randomness. So in this case, so this just means that there are a set of spatial points that you can sort of take as a basis. I mean, it's not really a basis, but you can write every point as a linear combination, or in fact, convex combination of them. And to be sure, it doesn't mean the boundary, right? Because here, about the boundary of a triangle would be the whole thing, would be that these 3 lines, but extremal points here is just these 3 points. And they're extremal points precisely because everything else can be written as a convex combination of these 3. So like you can have, for counterexample to this, you can have convex set that are not bounded. For example, like a cone, like an infinite ice cream cone. So the so if this is closed here, the extremal point would just be this tip, and then like the boundary of the circle, right? But if it just go on infinitely, then yeah, the points inside this cone cannot be written as a combination of extreme points. Or if the set is not closed, so if I have just some open set in like R2, for example, then every point in this should be you should be able to write in terms of convex combination of things in the boundary, right? But if it's an open set, then the boundary is not in the set itself. Yeah. So this is pretty spatial. What do I want to say before it's probably the time running out? Okay. Okay, if I remember, I'll say it next week. So in quantum mechanics as well, that I can think of taking convex combination of quantum state. So we're changing to the new mindset, and we say that every states that you can write as a state vector are pure state. You just did not declare it by fiat, right? So it's the same, doesn't matter if you write as a vector, as a one-dimensional projector. Every state that you know now is they're just pure states. And then you can consider taking a convex combination of pure state where this thing works like a probability but not quite, but it's still true that these are convex combination, right? M basically can be anything, can be any integer. In particular, it's not restricted by the dimension of the Hilbert space. This can be greater, it can be infinity, even if you're in like the qubit space. And we'll talk more about this next week. And part of it, we'll talk about why it's a bit misleading to call this probabilities. But for example, can you think of some reason of why it shouldn't be called probabilities? Because the usual way that people like to introduce mixed state is that they say, okay, I have there's some guy that's not me, and then he prepares some quantum state, but I don't know which one. So maybe that's probably the P1 to prepare this, P2, P3, but I don't know what he actually prepared, and then he sent it to me. And then they say, okay, this state should be described by this mixed state, this mixture, which is true. However, the receiver, so I got this rho, this operator. So by the way, it's called density operators or density matrices. The reason for the word density is the same reason that is used the symbol rho, because some like I guess one-eye man introduced this, and he think of it as an analog of density in phase space. But say, yeah, I am given operator, the state that's described by the operator rho. But why would I? What would be the problem to think about this P as being the probability? Well, maybe the first question is probability of what? But then if you can pin down what that would be the probability of, and then you then maybe you can think about, well, whether that interpretation is always valid or not. Okay, so I guess maybe we end this lecture, maybe make it more clear. and well, maybe just for today. Uh, เรียกว่านายกแล้วกันหรือนายก Okay, with probability pk, and that is one interpretation. There is probability pk that we can find the state to be psi k. And in classical probability theory or classical world, we think of these two as the same thing, right? Yeah. And for quantum, the first one is valid in the sense that there's a causal direction here, right? That someone has some uncertainty, and he prepared this state, and then this is the uncertainty of the receiver. Well, so of course this guy knows what he prepared. Well, unless he prepared a state and he got knocked out or something, and then he wake up with some memory disappear, some memory missing. But there's something fishy going on with the second interpretation, right? Can you say that pk is a probability that when you receive rho, you can find psi k? By the way, this is the last question. So sorry. Well, trace rho is, well, we'll see. It's always a 1, but it doesn't depend on k, right? It does. We have phi 1, phi 2, phi 3, for example, phi 1 have 2 ตัว phi 2 40 ตัว uh-huh. Uh-huh. And then that drawing so yeah, when you throw it in the box, then it's okay, right? So I throw like, yeah, I throw something that's close to P1, P2, P3 of these pure states into the box. But when the other guy, Nai Core, when he get it out of the box, do you think that we actually get like each state with let's see. Yeah, so that is one interpretation. But can he actually find out? Like in the sense that, okay, if I get psi k, how do I know that I get psi k? Well, I guess in the sense that yeah, Nai Kor would like bring the state out of the box, and then he will try to get something that's like a frequency corresponding to like each state, right? But how does he know that this is the state psi k? Yeah, so I think that's it for today. We can cut the camera and continue to discuss if you want to. Yeah. Thank you. ยังไงเอ๊ะเคลียร์วันนี้เลย